So let's try to do some. I brought some problems over here. Let's do this together. So we have. Oh, actually, this is not. Okay, so we have. This one. And so we have several numbers of equations. We're going to use Hester's law to just predict the final equation enthalpy change. So this is now this problem. So we have three equations with each that has enthalpy change. And the final equation we want to look for the enthalpy change is this one. So the question is if you know the enthalpy change for each steps, maybe using the Hess's rule, we can try to find out the enthalpy change for your final equation here. So whenever you have a problem like this one, what you can try to do is you can try to look for the position of the reference and the products on the final equation. So this is the key point we can start with. So for me, if you have a NO, nitrogen monoxide here, in this position left and left, so I'm not going to change the position of these two. Okay? So this is just okay to just stay there. And also, if you look at this O3 ozone here, which is not here, but we have a one on here. So if you just add these two together, you're going to have a 2O3, which we don't have. That happen. So what I'm going to do is I'm going to flip this one in here. Then you need to multiply this number by -1, because now it's going the reverse reactions. Okay. So if you do this one, you're going to have now it's heading this way. It's heading this way. So I'm going to actually do the same thing for this one, because on the final equation over here, we have a O here, but you have a 2O on the right side. So whenever you want to add all the equations here together, it has to be located on the left. So for the same reason, I'm going to just flip this one again here. So I'm going to multiply this one by -1. So the thing is, we have a O here, but in the final equation, you only have only one O. Okay, but there's two O here. So what I'm going to do is I'm going to divide this 2 by 2, meaning the coefficient number. So 2 divided by 2 will be just 1. And there will be 1. You don't see it there, it's implied, but 1 over 2 is what? That's half. 1 over 2. Okay. So meaning you also need to do the same thing for this one. So now it's multiplied by -1. So now it's negative. And you also need to divide this one by 2. So we're going to do the same thing that we do for each equations on the steps. And then if you do the sum, what happens to this one is this is on the right side, this is on the left side. So this will be canceled. We're happy because we don't see that O3 down here, which is the perfect. And then we can have this one down here, which is also good. This is what we want. This is down here, which is good. And we have a 1O down here, which is on the left side too, so it looks good. For O2 here, this is the 1, but there will be 3 over 2 O2, and there will be 1 over 2 O2 here. So if you do that all, you can add them all. This will be plus 3 O2 O2, and this is a plus 3 over 2 O2 too. Okay, but like I said, if you have the same thing over on the left and right side, you can also cancel them together. Okay? So this will be gone. So finally, we have an equation what we need. And to do that, we just need to add now these all together. So we didn't do anything for this one, so I'm gonna keep the same number as it was for the first one, but the second one we just flipped it. So I'm gonna put the multiply by -1, so it will become positive. Okay, so it will become positive, and we was initially positive. We flipped it, so it will become negative. But further, we actually had to half of these two, left and right. So we divide by 2. This would be 247.5, right? Yeah. And then you add all these together. So keep the negative sign, plus sign, everything, negative sign here. Okay, so some people confuse. If you do this one, it will be minus. No, we just plus. So it will be minus, plus, minus. So it will be, yeah. So this means what? 109, okay, plus 142.3, okay, and then plus the minus number will be the minus, right? Minus 247.5. Okay. So that will be your answer. Okay. So obviously, this will be what? Very wrong process. I think this will be too complicated. But this is how we can do it anyway. Even though you have multiple numbers of equation, once you look at the final equation here, you can try to sort out the position of these rectangular products and flip it, and do the same thing for the enthalpy change. And if you sum it up, you can do the same for the enthalpy change for each. You can get this one here. So let's try a problem one more, which I think more likely on your exam. So maybe this one may be not on the exam because this is too long and too complicated. So maybe you can try this one. Should be something you may see in the exam more, right? Okay. This time, it doesn't change. Okay, and the final equation I want to make is this one. Okay, and then what might be the entry change for this one? This is something you can try. This will be quite easier, I think, because you only have a 2 equation to kind of balance for your final, and then just try to find out if there's anything you have to cancel or flip to get the final equation here, and make sure you guys do the same for those numbers and try to add them all together to get the answer. Okay, about 1 minute, 1 or 2 minutes. We'll do this together. Okay, about 30 seconds, we'll do this together. So try to see where those are on the final. So you always start with the final equation, that's the start point. And try to see if you have to flip any one of those two or anything, and you can add them all together. Okay, so here's the thing. So if you look at this one over here, always looking for the ones on the final one. Okay, so you have a hydrogen peroxide on the left, and this is where you can find it. It's already on the left. So meaning you don't have to flip this one because this is where you want it to keep on the final, right? Okay. So this is one here. Is water is also on the right side, and this is where you can find it on the first one. So meaning you also don't have to flip this one either. Just the way it is good. But the thing is this O2 here. But the thing is, if you get down to, so you can keep this on the left, on here, O2 here. But if you look at this one as like a 1 is equal to what? 2 over 2, right? 1 is equal to 2 over 2. You have a 1 over 2, half of the O2 is there. There's 1 O2 here. So you can also cancel, but not whole because it's only half. So we'll just go down to half of that as well. So this is how we get the final equation. So technically speaking, what? We didn't do anything here. So you just need to what? Add these two numbers. That would be what? Negative 98.9. Okay. It's pretty easier, right? I think this is a lot easier. This might be something you probably see more. Maybe not too long. Okay, let's try one more, and then we'll move on. Okay. Okay. You can try to do this one, or maybe you can have a bit more idea of what's that like. Okay, this is the first one. Second one is. The final equation we're looking for is this one. And just try to get the enthalpy change for the final one. Okay. Okay, about 1 minute, 1 or 2 minutes. Okay. All right, so let's do this together. Okay. So if you have a 1 and 2 over here, what I'm gonna do is also I'm gonna start with the final one over here. Okay. So we have a carbon over here on the left side, where you can find in number 1, but it is already on the left. So what I'm gonna do is I'm not gonna flip this one, the first one, because you already have the carbon on the left. This is the way we want it to be happen to your final equation here. But the second one is a bit different because you wanted to keep the water on this side, which is on the left on your final equations, but it's on the right here. So that means we have to do what? You have to do flip it. Okay? So I'm gonna flip this one, and then whenever you flip it, make sure you multiply your enthalpy change that by -1. Okay, so I'm gonna do that and see what happens there. So we have this one here, which is good, We also have O2 right here. Okay, so we have O2 here. The O2 here. So we have carbon dioxide, this is on the right, perfect. We have 2 hydrogen gas molecules, so it's pretty good. O2 is also here too. But once again, if you have the same thing on the both sides, you can cancel each other. So this is how we got the final equations. So technically what you need to do is just multiply this number by -1. So then become positive, right? So it's negative, it's positive. And then you just need to what? Add them all together. Okay? And that would be your answer for this one. Okay? Makes sense, right? Okay. All right. So this is pretty much it. I think those only 2. The step equations for this type of a question. If you can match it with the final one and do the same thing for the each and do the sum, and that will be the trick. There's a way to solve this type of problem. All right, so on Wednesday we talked about the chapter 6. So chapter 6 was about the structure of electronical structure of the atoms over here. So we talked about the speed of light was actually lambda times mu, was wavelength. This is wavelength in meter, okay? And this is a frequency per second. Okay? So there's one thing I want to tell you is that you have hertz. You know what this hertz? Like a megahertz, like in a radio frequency. You heard it, right? This is the same as per second. So hertz means per second. So how many things happen per second as a hertz? Usually your radio station uses a megahertz. Megahertz simply means what? The mega means a million. Okay, so it's a millions per second. That's what the frequency is in the radio. So radio is usually very, so you see it's a lot of big number, which is actually not compared to the visible light range. This is not so frequent, I mean not waving frequently. So radio is quite safe. But the good thing about the radio is whenever it waves less than the normal, either visual light or the UV light, it can go further. So which is good for the radio. So anyway, we have this one here, and we are about to do this one. So this is energy. It should be equal to Planck constant. Planck constant. And times frequency. Okay, so this is what we are about to do. So this speed of light is always 3.0 times 10 to 8 meter per second. Okay? So what we can possibly do, we actually did how we can use this one. So if we have some light at the certain wavelengths in nanometer, you can convert the numbers in maybe meter, because you have to express the speed of light in a meter per second. So the nanometer equal to 1 times 10 to negative 9th meter. So 300 nanometer means 3.0 times 10 to negative 7 meter. Okay? So you actually get this a lot because we're going to use hundreds of nanometer for the conversion for the wavelength because this is the kind of range where you can see the visible light. So either 300 to like 800, you're going to see this number a lot. So what I normally do is you have maybe 350 nanometer wavelengths. I just know it's 3.5 times 10 to negative 7 meter because I did it so many times, and you actually get this soon because when you're gonna practice this one here. So if whatever that the wavelengths you have for the light, you can actually solve for the other one, which is a frequency, because this number is fixed at a certain condition, as I mentioned on Wednesday. So this is what we did last time. And then we're gonna do is this one. This is energy of photon. This is the energy of 1 photon. So photon is like this one. So we actually learning about the quantum mechanics in chapter 6. You're gonna learn about something that's kind of really weird. The one of them was the like Schrödinger's cat and dual nature of the light we discussed on Wednesday. But the quantum simply means a very simple thing. Quantum means a minimum unit of something. So the photon is the minimum possible unit of the light. So if you have a certain light goes into space, it has to be at least more than 1 photon. So if there's less than 1 photon in the light, it's not the light anymore. There should be the minimum requirement for the thing to be the light. So the quantum of the light is photon. We kind of treat the light as a particle. So minimum particle of the light we can talk about is 1 photon. And that amount of energy is actually coming from this Planck constant times frequency. Frequency, okay? So the Planck constant number is this one, 6.626 times 10 to negative 34. Okay? And this is in joule times second. Okay? So this is why whenever you multiply this number by the frequency, which is what? Some numbers in per second, right? And then you're actually going to get the number in joule, which is energy. Okay? So this is in joule times second. So times the frequency will be the energy of the photon. Okay? One photon. Okay? Does it make sense? Okay? Okay. So I'll give you one example here. Okay, let's try this one together. So okay, so maybe if there's a light that shows its frequency about because frequency is about maybe 2.10 to maybe 14 per second. Okay? And what might be the one photon energy? That's the question here. Okay, so here's the same. So like I said, we're going to use the Planck constant, which is 6.626 times 10 to negative 34 joule times second. And then I'm going to multiply this one by frequency, just following this one. Okay, just multiply that Planck constant by frequency. That will give you the number for the one photon energy there. Okay, so I'm going to multiply this one by frequency, which is 2.0 times 10 to 14 per second. So if you look at this unit here, this is joule times second, this is time by per second, so this will be gone, and it will give us number in joule over here. Okay, so what you can do is the 6.626 times 2 should be about 13.3, something like this, and then this one is negative 34. This is multiplied by 10 to 14, right? That's same as what? Plus 14 here, okay? So that's a 10 to what? Negative 20th. Okay? So this is a simple way to calculate it. Oh, I mean, you can put it in the calculator, obviously, but maybe you don't have to. So anyway, so in this way, you just want to put the decimal point right after the first non-zero digit number for scientific notation. So I'm going to just move it to here, okay, and then I'll make it to, okay. So it will be 1.33 10 to negative 19. Because we move this one into this one, it's plus 1, so negative 20 plus 1 is negative 19. Okay, makes sense, right? Okay, good, perfect. So maybe you can try this one. Maybe you can try this one. Okay. What's the one photon energy? Okay. And Planck constant is 6.626 times 10 to negative 34 joule times second. Okay. My writing is not so good today. So about 2 or 3 minutes. It takes some time, right? Yeah. I mean, you can just put it in the calculator. There's no problem. But okay, 1 or 2 minutes. We'll do this too. About 1 minute. All right, so yeah. So we're just gonna do the same thing, right? So 6.626 times 10 to the negative 34 joule times second. We're gonna multiply that by the frequency, which is 3.3 times 10 to 14 per second. So now this is gone, and now we have a number in joule, which is energy for 1 photon. If you just do, I mean, you don't have to know, but if you just do 2, so it's about 2.0 times 10 to 20, and this is about 20 again, but you can do 2.2 and 19 instead, okay, for scientific notation. Did you get it right? So can I move on? Yeah.
On the test,
Mhm.
will you give us like a pre?
Yes. Oh, that's a very good question. Thank you. So those Planck constant numbers, maybe speed of light, and those constant number will be given. Yes. Then you can so either you can have a frequency, and this number will be given. So you can just plug that, and you can get it. So yeah, you don't have to memorize those constant number. It will be given on the exam. Okay. That was a very good question, actually. That's right. You don't have to memorize these. Okay. So can I move on? Okay. So just one more thing from here I want to do is sometimes I will not give you the frequency, but I will give you the wavelength. So for example, this light is at maybe 600 nanometer wavelength, and you're questioning, what do you mean? I don't have a number for frequency. How can I get a number for the 1 photon energy? We're going to use this equation over here. We have a C equal to lambda frequency over here, right? V. And then this is the same as this one. This one. I just moved this one to the other side, wavelength. So that makes a speed of light divided by wavelength will give you the number for frequency here. Okay? So we can do the same here. So E equal to constant times frequency, right? And it is also equal to Planck constant times C over lambda. Because these two are the same thing actually. Okay? So in this case, what you can do is, it's actually pretty much the same. I'm going to copy the Planck constant, joule per second here. And then instead of frequency, I'm going to multiply by the speed of light, which is 3.0 times 10 to 8 meter per second. Okay? And then we're going to use the wavelength, which is 600 nanometer, but I'll just do it brief. 6.0 times 10 to negative 7 meter. Okay, you know that, right? Okay, so meter. You make sure you guys do the unit conversion, because this is in meter, so they can be cancel each other, and this will be canceling this way. Okay, so in this way, you're actually going to multiply. So 3 over 6 is what? 0.5 times 8 over. So this is 10 minus 7 is a 15, right? Okay, 15 here. Okay, and I'm gonna move it to now on the right. So, and then gonna put minus, right? So there will be 5.0 times 10 to 14. Okay, so now we got the frequency by doing this, and now the job is done. You just need to multiply these two. Okay, so if you do this, this will be approximately 3.3 times 10 to 33.2 something, and then this is still negative 20. But I want to move this point right here, so it will be 3.3 times 10 to negative 19. Okay, so we got the number there. Yeah.
Can you do another one? But
Yes, absolutely.
Can you
Okay.
like go slower?
Oh, absolutely, absolutely. So, well, actually, what I'm gonna do is I'll let you try this one first. I'll do this together. Okay, let's try this one first. Okay. So once again, you only need to do this one, right? But you don't know the frequency, so we're gonna do this one. Okay. And then the C is the speed of light, which is 3.0 times 10 to 8 meter per second. And the lambda has to be converted into the meter. Okay. And then this the Planck constant is 6.626 times 10 to negative 34. Okay. So if you convert this one to what? Meter, it will be 3.0 times 10 to negative 7. Okay. So this one divided by this one times by what? Multiplied by the Planck constant, that's your answer. Okay, I'll give you about 1 or 2 minutes. You can try to plug all the numbers in and see if it adds up pretty well.
C is 3 times 10 to the.
Yeah, eighth, yes. Sorry. So, perfect. So I'll give you about 1 or 2 minutes and plug all the numbers in and see. Yeah. Obviously, you can do this in the calculator, but if you don't like to do that, you can follow my way, like I showed you. Okay. Wait 1 minute. So yeah, actually, if you know the trick, you don't need to use a calculator much. So it'll be even easier actually. So thing is here, if you do 3 times 10 to the 8th over 3 times 10 to the 17th, 3 over 3 is just 1, right? And then this is 10 to the 8th, but divided by negative 7. So that's 10 to 8, but negative, because it's a dividing. If it's multiplying, it's positive. But it's you negative of negative 7, so it becomes actually 15. So if you do this one, 1 times 15 here times this 1 times the 6.626 is the same. And then this is 10 to the negative 34, right? Negative 44, multiplied by 15. So it'll be plus 15 right there. Okay. So then will be 10 to what? Negative 19 in joule. Okay. So I think this will be easier for you to calculate. You can actually put it everything in the calculator. The thing is, you have to put the exponential number on the 10, put the brackets and dividing it. So you may have some errors in the calculator if you put it just one parenthesis, one exponential number wrong. So that's kind of unfortunate, right? So if you can. All right. Okay. All right. So I'll definitely do more problems like this before exam 2. I'm planning to have at least 2 review sessions on this coming Friday and also the coming Monday, because we're gonna have the following week of the Wednesday and Friday. So don't worry about it. Just keep watching the either video or do the problems. We'll do this together in review session again. Okay? Sounds good?
So you said next Friday and then Monday?
So yeah, so what day is now? So we have this coming Friday and the one after, the Monday, we can have at least 2 review sessions. So we should be plenty of time to just go through the review. So we'll also do that too. Yeah, perfect. Because the exams on Wednesday, Friday. So all right. So the next one is there are a couple of things I just want to mention. This is kind of something you may have heard before. This is Heisenberg uncertainty principle. That simply means this one. He actually proved this equations. This one. So what it really means is you don't really have to worry about this number here, which you can say is just one number there. The thing is a change in position. So x means the position, coordinate in the coordinates. And this is like a momentum, but in the change of the speed or the velocity actually. So the momentum or the momentum change or the change in the position of the particle. So I'll show you. So positions of particle, a particle, non-particle, you can say. And momentum, or you can say just speed or the velocity. That should be just fine. But you can say more precisely momentum of the particle cannot be measured at the same time. Oh man, sorry. So once again, I'll just say the position change or the momentum change should be greater than at least certain number here, which you see here. That is why because of this position of the particle or how fast it's moving in the space cannot be measured at the same time very accurately. It can only measure by either one very accurately, the other somewhat less accurately. They can be actually measured, but they cannot be measured at the same time very precisely. No, because of this one. There's one analogy I can give you is this one. Do you guys like to take a picture? You guys take a selfies and stuff, right? Here's the thing. So if I do this like I try to take a picture of something that is moving, but if you have some like a moving stuff, unless you have a really, really good camera, if you take a picture, what happens is that you're gonna see the after image, right? And it's really moving fast. You know that, right? So if you look at the picture, if you look at how far your after image of that moving object, you can actually estimate how fast it's moving, right? Because you search the after image. But if you have a really, really good camera, even though it's moving really fast, you can actually take a picture. It shows like almost like a still picture. If it's a really good camera, then you know where your hands is, but you can't really tell how fast it's moving. Okay, so that's something you can think of. It will kind of make sense. I'll just move on. Okay, but just remember this rule: the position of the particle or the momentum of the particle cannot be measured at the same time precisely. Maybe either one is precise, the other is not so accurate, and so. All right, let's move on. Okay, so the other one is the de Broglie. I think it's de Broglie, the matter wave. Okay. So what he's saying is kind of interesting because he used the Einstein's equation, mc squared, right? And then we actually use this one to move it again. Okay, so we can try to move this one again with you can try to move this one, this c squared. Do you know what c stands for is right now? Speed of light, right? This is the mass in kilograms. And then he tried to use this one, then you can be energy over c squared will be the mass, right? And then, as we know, the energy is equal to what? Planck constant times frequency. And frequency is equal to what? C over lambda. Okay? So if that is possible, you can cancel the one of them. And this is one of the lambda, so you can actually make it in the balance there. So the Planck constant over speed of light times its wavelength, that shows the mass over here. So if you do that, you can actually switch it. So the wavelength can be determined by the Planck constant over the Cm. So this is a mass in kilograms, and this is the speed of light. But he actually generalized the speed of not just the light, but for everything. So this could be any matter that has this much of the mass, and then this is the speed of their this is the velocity. So velocity of that matter And so Planck constant over that velocity of that matter with that mass of the matter can show this much of the wave. So what it really means is, you learn about do you guys remember, I don't know if you watched the lecture on Wednesday, it actually means the light has a dual nature, right? It can behave like a wave, sometimes it can behave like particle, like a matter. And Du Bois was like, it's not Berkeley, it's actually French, I think. Anyway, the Du Bois actually said maybe not just the light, maybe everything, every matter has also not just the particle, but it has a wave property as well. Not just for the light, because light shows the dual nature. And then maybe he said, oh, maybe even electrons or the molecules, even our body, maybe have a big chunk, also have a wave like this, which still be very, very small, because compared to the electrons and the photons, you'll be very big in size. So you can easily notice that the wave, but still be there and this thing. So it's kind of ambitious approach to the matter even can show the somewhat wave property, even though it doesn't seem so very like remarkable, noticeably, because we're too big. But yeah, I'm sorry. Does it make sense? Yeah, I'll just move on. This won't be on the exam. I don't think I'm going to put this in the exam. So okay, just move on. All right, so there's a couple things I want to discuss. Just looking at the clock, I don't think I'm going to make it, but let me just briefly explain. We're going to learn about how the atoms can emit the light in form of energy, in form of the light. But before we get to there, we're going to do the quantum numbers. Okay. Quantum numbers. There are four numbers. There are four numbers there, and three of the four is for indicating orbitals. Okay, orbitals, and then the last one is for the electrons in orbitals. Okay. So orbital simply means this one. Have you guys heard orbital before? Yes. Okay. So orbital is kind of funny thing. The orbital is not the real matter. So orbital is the imaginary space where we think that we can possibly find the electron by high chance. So if there is some like a orbital around the coordinate here, this one is materially does not exist, but it's just mathematically constructed by human that we just think, oh, there might be some reason where we can possibly find the electron by high chance. That is orbital. So we're gonna talk about the orbital sometime soon. But there are three numbers for the quantum numbers for orbitals. We're gonna indicate last one for the electron later. The first one we're gonna discuss is the principal quantum numbers. So we actually denote it as n, small n. The next one is angular momentum quantum numbers. We actually put it as L. The third one is so this is the first one, second. The third one is a quantum number, magnetic quantum numbers. So those are three are for the orbital, what kind of orbital you have. The last one is a magnetic spin. This is for your electrons in the orbital. So this is actually in the ML. This is an MS. This L is actually subscribed under there, and S is as well. So M is still small letter, but it's subscribed. E, like this. Okay. So I'll just do this on the Monday. Okay. So stop it. But we're gonna do this one on Monday. We're gonna use it for the Lineberg equation. Okay. Let's stop here today.